one thing that we haven't really thought about yet is what's going to happen if more than one indistinguishable photon enters into a beam splitter. So it's unclear that we've really maybe have the machinery yet to determine what would happen if we have some beam splitter where we have, say, m indistinguishable photons entering into this top port and n indistinguishable photons entering from the side port. And of course, in the real world, this could happen in experiments, so we might want to know how to model this. So one way we can approach this is by looking at how the operators for creating and annihilating photons are going to change due to the action of the beam splitter. So basically, we can consider the action of the beam splitter to be some matrix U, which could either act on the incoming state or could transform the operators which can create photons in the incoming state. And the operators that we want to transform, these are these A and A dagger and B and B dagger operators. And these will just describe creating and annihilating photons. So this operator A will annihilate a photon that would be entering in port 1. A dagger will be creating a photon that would enter into port 1. B would be annihilating a photon that would be entering into port 2. And B dagger would be creating a photon that's entering into port 2. So we can create any arbitrary quantum state consisting of photons by just starting with no photons at all, the state of no photons at all, which is a vacuum state, and adding creation operators to that state. So this would mean that our end goal now is to find out how the unitary operator U, which represents the action of the beam splitter, will interact with and affect the operators A dagger and B dagger, for instance. So we want to be able to solve for U B dagger U dagger and U A dagger U dagger. And one way we can do this is, or the way that we'll do this today, is by just introducing an expression that's basically a guess for how we think this beam splitter is going to operate, and then we'll verify that this expression will basically recover the results that we would expect in the case of a single photon, in the case of single photons, which we've already found by using these transfer matrices. So in this case, our Hamiltonian, we can think of this unitary as being parameterized by a Hamiltonian, and the Hamiltonian here is going to be some coupling term G multiplied by A B dagger e to the negative I phi plus A dagger B e to the I phi. And phi is going to be some phase that we'll be able to interpret later. And then when we solve for the unitary, when we find how the unitary would act, we just follow Schrödinger's equation to find this. And then we'll see later that our theta, our mixing angle theta, is going to equal G times delta T. So if you go through and do all this math, and if you go through, do all the math and solve for U B dagger U dagger and U A dagger U dagger, it might be useful to use like the Baker-Campbell-Hausdorff theorem. But in the end, you can find these expressions for the transformed operators for the output of the beam splitter. And we can actually see that this will match up with our transfer matrix formalism for some special settings of the theta r and phi 0. But otherwise, this is very, very general.